What if you could unleash an atomic bomb on an entire city without actually killing anyone? Without obliterating buildings, without contaminating the land and its life with generations of radioactive poison. It promised the finality of Fat Man and Little Boy without any of the destruction. And it was so close to being implemented in the 1950s that it made the cover of Popular Science. But it wasn't about splitting atoms to release the equivalent of thousands of tons of exploding TNT. It was the carefully crafted deployment of radiological weapons that were perfectly engineered to be just right. Not too powerful and not too weak, loaded into an airplane and spread like a farmer's pesticide. You know the impact of the atomic bomb, from Oppenheimer to Godzilla to Akira. But now, declassified top-secret documents from both the United States and the Soviet Union tell us what really happened. It's the story of grasping at a new, terrifying science and trying to harness it to solve humanity's oldest problem. And it's the story of how we got death sand. In May of 1941, science fiction writer Robert Heinlein predicted the future so well that he didn't even know he was actually describing his own present. World War II had raged in Europe for nearly 2 years. It was more than 6 months before Japan's attack on Pearl Harbor. Writing under the pseudonym Anson MacDonald, Heinlein published a story in astounding science fiction called Solution Unsatisfactory, in which an unconventional weapons initiative attempts to solve global war by unleashing bombs weak enough to blow up only one county at a time and stable enough to blow up only on request. Then we would be in a position to make most anybody say uncle to Uncle Sam. The Manhattan Project would start in December of that year, but the Death Sand Project was already underway. Alden P. Armagnac's What You Should Know About RW, that's the abbreviation for radiological weapons, posed a question right on the February 1951 cover of Popular Science. Can death sand win battles? It described the potential for the US military and its allies to use their evolving understanding of nuclear weaponry to move beyond fission bombs and thermonuclear devices and into an era of more nuanced, more gentle nuclear war. Gentle nuclear war. Huh? Armagnac's article is more than 70 years old and it's only a few pages long. It's mostly pictures and artwork, but reading between the lines not only explains the entire history of warfare, but also offers a glimpse into our own present and future. It was essentially a summary of a 12-page government memo that made its way into Officer's Call, but to understand how we got radioactive death sand spread with a crop-dusting airplane, we need to start at the beginning. Literally, the beginning. In On War, Karl von Clausewitz described war as not merely a political act, but a real political instrument, a continuation of political intercourse, a carrying out of the same by other means, which basically means conducting diplomacy with physical force. Violence works exactly the same way with individual humans. When talking doesn't work anymore, well, there aren't too many other options. The very first Homo habilis murder probably happened when Clonk strangled Glork because he wouldn't share his turtle meat. The evolution of humans is also the evolution of physical violence. The pattern has 3 parts: effectiveness, physical distance for safety, and psychological distance. You want to do what you need to do as well as possible, as safely as you can for you, in a way that's the least personal. Clonk used his bare hands. When Cain killed Abel, he used a rock, which is more effective, safer when it's all over in one blow, and a weapon that's a little less you. Then it was clubs, then spears to project your will from further away, and slings that were less accurate and lethal but afforded much greater distance. Swords and other blades sacrificed that distance for greater impact, making the psychological trauma of both giving and receiving blows awful. Arrows got us even further away than artillery and guns and rockets and chlorine and now drones. We're almost playing Ender's Game at this point, applying far-off force through digital interfaces without even having to see the victim's face. And we really are. Just 2 years ago, Raytheon gave us a glimpse at a 10-kilowatt laser that used an Xbox controller to zap a DJI Phantom drone. On August 6, 1945, the Enola Gay dropped the Little Boy bomb from nearly 10,000 meters off the ground, and it exploded with a force of 15 kilotons of TNT with a blast radius of 1.3 kilometers. That too was in science fiction before it changed the world. H.G. Wells wrote in the 1914 novel The World Set Free of cities obliterated by atomic explosions. No one doubted the effectiveness of the atomic bomb, but what if you could get the same result without anyone even dying? That was the promise of radiological weapons, harnessing substances that would conduct Clausewitz's diplomacy by other means, using exactly the right level of radiation, and without necessarily blasting a city back to before Homo habilis and taking 200,000 or more civilian lives with it. To do that right, we needed to know exactly what radioactive material did to the human body. Medical physics professor Joseph Hamilton started testing the effects of plutonium on rats, but that wasn't good enough, so he injected 18 people with plutonium in secret. The trials were done at the University of California Hospital in San Francisco. Albert Stevens was known as Subject Cal 1. He was 59 and died 20 years later as having survived the highest known radiation dose in human history. Simeon Shaw was Cal 2, and he was just 4 years old. He'd been diagnosed with bone cancer and died less than a year after his injection. Elmer Allen, Cal 3, lived another 44 years, and Dr. Hamilton himself died of blood cancer at the age of 49. In the years after Hiroshima and Nagasaki, everyone was pretty much guessing about radiation. That also added a critical component to the use and the value of radiological weapons. Because uncertainty and unpredictability generate fear. If it's scary to us, it's gotta be scary for the other guy too, right? So how do you get a global authority like Popular Science to publish an almost optimistic account of radiological weapons? Well, the science was exciting, and the US government actually wanted people to know how it worked. In 1951, the acting Secretary of Defense wrote, "The Director of Public Information, Department of Defense, has been directed to undertake a program of public information in this field as recommended by the Noise Panel," which included a recommendation for using irradiated tantalum, specifically tantalum-182. Death Dust, The Rise, Decline, and Future of Radiological Weapons Programs actually contains a footnote about Armagnac's Popular Science article, that it's less polemical than other contemporary analyses. The authors refer to tantalum-182 as occupying the Goldilocks zone, meaning it was not only potent enough to be dangerous, but also didn't decay so quickly as to be ineffective or stick around long enough that it rendered the area useless forever. What's the point of not destroying buildings if they're too irradiated to occupy for the next century? It's not rubble and it's not uninhabitable forever, so it's like a nuclear timeout. Tantalum-182 had a half-life of just 114 days, so ultimately a form of temporary radioactive warfare. We think now in terms of weapons of mass destruction, nuclear dirty bombs that effectively poison a population and the land they inhabit, a modern version of salting the earth. But the value of a temporary radioactive tactic is revealed when you think about Alden Armagnac writing for Popular Science in February of '51, 8 months after North Korea's invasion of South Korea. It was the first conflict with severe international implications since World War II, and no one wanted to see a repeat of that war's destruction and tens of millions dead. Not the US, the UN, or the increasingly powerful Sino-Soviet communist bloc. They were thinking in terms of what military strategists call area denial, making it impossible for someone to be in a place. Area denial is what happened in the story of Scipio Aemilianus supposedly salting the soil of Carthage. He was denying the Carthaginians use of that area ever again. And while almost certainly apocryphal, it was probably based on the real raising of Shechem in the Galilean rebellion. But it's also what happens in scorched earth warfare, destroying the land to such a degree that the enemy can't use it, and especially sabotaging an advancing army like the Russians did with Napoleon and again against the Axis. This means a Goldilocks radiological bomb could be dropped in an area to make the enemy vacate immediately or make it impossible for them to cross the territory. So if you're South Korea, you could create a territorial force field the invading army couldn't cross. Douglas MacArthur even suggested bombing an impassable line, 5 miles deep and 100 miles wide, to keep out Chinese aid to the North Korean army. And why blow up a whole city when you can politely convince everyone to evacuate by coercing them with radioactive poison? That was the notion put forth in a 1950 Time magazine article in which Dr. Louis Ridenour considers radiation to be a rather humane weapon. If 2,000 rontgens of radiation constitutes a lethal dose and you spread radioactive dust at 2 curies per square meter, a human would absorb 8 rontgens per hour, meaning it would take 10 days to build up to 2,000. So they've got plenty of time to leave safely without being exposed to a level of radiation that would bring any damaging effects, and it gives each member of the target population a choice of whether he will live or die, as long as he flees at once with a folded, dampened handkerchief over his nose and mouth, which I guess is a little better than hiding under a desk. The nuclear arms race was a race, meaning that both the US and the Soviet Union weren't just trying to develop their own radiological weapons, but were concerned with RWs being used on them. Both countries had been thinking about being on the defensive end of radiation since World War II, when the US conducted Operation Peppermint to counter the possibility of Germany using radiological poisons on the beaches of Normandy to counteract the Allied invasion. The logistics of responding to the use of radiological weapons were really complex. You needed to be able to detect the radiation accurately to calculate its level of threat and the area of that threat. You needed to be able to move personnel and material away from a poisoned site with speed. You needed a strategic plan B when you were on the wrong end of area denial. If you couldn't vacate or go around, you needed suits that could withstand radiation, breathing apparatuses that were capable of filtering radioactive material, or a contained oxygen supply if they couldn't. You needed shielding, probably made of lead, for vehicles, and all of that added weight would consume more fuel than normal, and yeah. And if you manage to load that crop-dusting plane safely, flying it is dangerous. Armagnac wrote that thick, heavy lead shielding could be omitted if crewless planes under radio control from accompanying aircraft laid the death sand. So it was a vision of drones back when Alice in Wonderland was in theaters. The Soviets were open to anything. In 1947, Lavrenti Beria had just finished an 8-year run as Stalin's head of the NKVD, the Soviet Union's secret police. As deputy prime minister and curator of the organs of state security, he recommended to Stalin that radioactive materials, considering their resilience, can be used in times of war on a large scale as equipment for long and short-effect artillery shells, for an air bomb, for long and short-effect aviation, and finally, for sea mines and torpedoes, similarly to how they're used as poisonous material for chemical ammunition. Their method of delivery was called Solution 904, spent nuclear fuel that contained zirconium-95 and niobium-95, which the United States was also using in its radiological weapons development. They had some theories and they conducted experiments, but the testing never really advanced. At one test launch, a warhead began leaking brown liquid. The testing team ran from the radioactive danger, but the scientist in charge wiped his finger through the stream and licked it. He said, "It tastes like crap, but it's harmless." Soviet popular culture did have a recognition of radiological warfare and used it as propaganda targeting the United States. Abram Room's 1953 film Serebristy Appeal, which translates as Silvery Dust, depicts a crazy scientist from a rural Alabama town who invents a weapon that can spray lethal radioisotopes, which he tries to sell to a capitalist member of the US Nazi Party. But death sand and silvery dust and all its radioactive cousins ended up being pretty harmless in the sense that no one's actually used any of them. The costs were enormous, not just because it was all atomic science, not putting baking soda and vinegar in a plastic volcano, but because it was a substantially different kind of research and development than the large-scale fission and thermonuclear required. Different materials, separate facilities, entirely separate projects. And if you're paying a lot for the major thing, how can you justify the continuation of an equally expensive minor thing? In American Biodefense, Frank Smith writes of the kinetic frame, that militaries and leaders have a bias toward weapons that are similar to conventional weapons and against new technologies. So, generals understand big bomb, go boom precisely because we've been doing it for hundreds of years, and they're way more wary of something that just got described in astounding science fiction, especially when it's a solution to a problem that you can already solve. Militaries knew how to use their conventional and increasingly effective weapons. They didn't know how to use radiological weapons, and they didn't even know how to control them. A 1949 prototype test at the US Dugway Proving Grounds found that the radioactive material extended over an area 50% greater than anticipated. Playing a dangerous and potentially catastrophic radiological warfare game just wasn't worth it. But it turned out that not everyone cared about using powerful weapons with restraint. As president of Egypt, Gamal Abdel Nasser pursued radiological weapons after the Sinai War, and he was comfortable using cobalt-60 with a half-life of 5 years and strontium-90 with a half-life of 28 years against Israel. And in the mid-1990s, inspectors uncovered Saddam Hussein's experimentation and testing for radioactive area denial weapons to counteract human wave attacks in the Iran-Iraq War of the 1980s. Now the threat from radiological weapons comes from non-state actors, and it's because we've talked so much about them. It's called the deterrence dilemma. When you publicly discuss the effectiveness of a weapon to deter others from harming you, you kind of make your enemies more interested in using that exact weapon against you. One of Al-Qaeda leader Ayman al-Zawahiri's computers seized in Afghanistan contained a document about biological weapons which said, "We only became aware of them when the enemy drew our attention to them by repeatedly expressing concern that they can be produced simply." And the prospect of an unbridled dirty bomb has fueled propaganda from Russia, who spread information accusing Ukraine of hiding the development of radiological weapons in the already contaminated Chernobyl area. And from Ukraine, who has voiced concerns that Russia could detonate the Zaporizhia nuclear power plant to make a giant de facto dirty bomb of their own. Heinlein's story was science fiction that was virtually indistinguishable from reality. The solution was an exceedingly powerful weapon and an entire industry surrounding it. It was unsatisfactory because there's no going back. Not from using it, and not from threatening to use it. Not from inventing it, and not even from advancing science to a point where we know it exists. T.S. Eliot's 1922 poem The Wasteland was published 4 years after the conclusion of what was to be the war to end all wars. A decade before the Cockcroft-Walton machine split the lithium atom, and nearly 20 years before the Manhattan Project began. The Wasteland contains 5 sections. The first is the burial of the dead, which describes a barren, uninhabited desert of endless sands. A dead tree gives no shelter. In a dry stone, no sound of water. There is only the prospect of one's shadow behind them in morning and in front of them in evening. Eliot writes, "I'll show you fear in a handful of dust." See you in the future.